Hey guys, welcome back to chapter 13. Today we're going to continue talking about those examples where we know initial concentrations, we know the equilibrium constant K, and we have to fill in our ice table with a bunch of X's. But I'm about to make your life a little bit easier. While the quadratic formula will always work, that'll work 100% of the time, every problem you ever encounter. There are some problems that allow us to do some shortcuts, some easier ways to solve it. So that's what today's video is going to introduce is your first shortcut to solving these. So like I said, with these types of problems where we fill in our ice table with X's, the quadratic formula will always work 100% of the time. But there's also two other shortcuts that we're going to talk about and learn. The first one is something called the perfect square, and that's what this video is going to address. And then in another video, we'll talk about simplifying approximations, or when I learned it, it was called X is small. So you'll hear me call it X is small as well. But today's about perfect square. So what we're going to do now is we're going to start to solve a problem. And before we get too deep into the quadratic formula, I'm going to stop us and we're going to take a look at how perfect square situations can be helpful. So here's the problem. If you guys want to give this a shot, you can go ahead and work it out to the point where it says K equals, and then you put in your values for products and reactants with the X's, and then stop there and let me catch up to you. All right, so we're going to work this one out. So the problem is if 1 molar hydrogen and 1 molar bromine are both added to a flask, how much hydrobromic acid will exist at equilibrium? So we're given initial values, equilibrium constant K is up here in the top. We need to know how much hydrobromic acid is going to exist at equilibrium. So the first thing we're going to do is we're going to draw our ice table. We're going to put our reactants and products on the top. So hydrogen, bromine, hydrobromic acid, and I like to put the coefficient in there. All right, initially, if we had 1 molar hydrogen, 1 molar bromine, so 1. No mention of hydrobromic acid, so we're going to assume that that is 0 to start. No information about change, so that's all we got, right? So now we need to start filling in our ice table, but unfortunately we're going to have to use X's. So looking at this, I see that my product is 0, so there's only one way for that to go, and that is up. So this is going to be a positive change. If my product is going up, then these two are going to have to be negative changes. They're going to have to go down. We use those up to make the product, right? So both of these are going to be minus. Right, so now to figure this out, we've got our coefficient of 2 here in front of our hydrobromic acid. So I know that this is going to go up by a value of X. Specifically, it's going to go up by a value of 2X. And each of these are going to go down by a value of X. Now that we've got X's into our chart, we can go ahead and fill in equilibrium, albeit with letters. So X, oh, no. 1 minus X, 1 minus X, and then this is 2X. Letters, we can plug that into the K equation. of products over concentration of reactants. And now we can plug in what we know. So 0.018 equals, so hydrobromic acid at equilibrium is 2x squared. And then our reactants are 1 minus x and 1 minus x. So this is that moment where we can kind of pause and decide if there's a shortcut. And in this case, there is. So I want to rewrite this bottom portion. So 1x squared times 1x squared. What's another way to write that? Well, let me come up here and maybe do something different. If I had x times x, what's another way to write that? Yeah, it's x squared. So this is 1 minus x times 1 minus x. Those are the exact same variables. So another way to write this would be 1 minus x. So you could take this into a quadratic formula problem. You could FOIL the bottom. You could get the ax squared plus bx plus c, and you could put it into a calculator. Or you could recognize the following. I have a squared value on the top. I have a squared value on the bottom. If the top is squared and the bottom is squared, this is a perfect square scenario. I can take the square root of this side. The square root is the inverse of these guys, so they go away. It has to have a squared on the top and a squared on the bottom and no other values in there. In true algebra fashion, whatever I do to the right side, I also have to do to the left side. And we can fathom taking the square root of an actual number. That's easy. We plug that into our calculator. So moving forward from this step, what do we have? So over here, I took the square root. That's the inverse of squared. So all that is left on top is 2x. And all that's left on the bottom is 1 minus x. No longer is it quadratic. On the left-hand side, we plug that into our calculator. So I take the square root of 0.018 and I get 0.134. Now we still have some algebra to do, right? It's not finished, we're not complete. But now we have basic algebra, not quadratic algebra. So I'm going to skip to the next slide so I have some room to work here. So where were we at? We had 134 equals, we had 2x and we had 1 minus x. What I'm going to do is I'm going to get that 1 minus x out of the denominator. So I'm going to multiply 1 minus x, 1 minus x on the bottom, 1 minus x on the top. Those cancel. Whatever I do to the right side, I also have to do to the left. So I'm going to multiply this by 1 minus x. I'm just doing it in green so you can see my work. All right, so left over here on the right side is just that 2x. Over here on the left side, I'm going to distribute this through the parentheses. So we've got 1 times 0.134. So that is 0.134 minus 0.134 times x. So that's 0.134x. Now I want to get my x variables on the same side. So because this is not quadratic, I do not need to get a 0, right? I'm trying to just simply solve for x. So now I want to move this x variable over to the right-hand side, so those are together. This is addition and subtraction. So to get this x variable to the other side, I'm going to add. I'm going to do the inverse. So add 0.134x. Those are the inverse of one another, so they cancel. Whatever I do to the right side, I also have to do to the left side. So plus 0.134x. So now what we have is we have 0.134 left on the left side. And when I add these two together, it's going to be 2.134x. And now I want to get x by itself. So I'm going to divide by 2.134. Number on top, number on bottom, that cancels. Whatever I do to the right side, I also have to do to the left side. So now we can solve for one value of x, and that's going to be 0.134 divided by 2.134, and x equals 0.063. We're not done yet. That was x. That was the big part of it. That was the hard part of it, but it's not the end. So now we need to take this value, and we need to go back to our ICE table. So we solved for our value of x. We said x equals 0.063. But ultimately what we are asked to solve for is hydrobromic acid at equilibrium. So this guy right here. So to complete this problem, we actually have to multiply by 2x. So the concentration of hydrobromic acid at equilibrium is 2x, which is 2 times 0.063. The concentration of hydrobromic acid at equilibrium, 2 times 0.063, we get 0.124 molar. Summarize, once we started plugging values into that K equation, we noticed that there was a squared value on the top and a squared value on the bottom. That's a perfect square, so I can take the square root of the whole thing, and that makes this much easier to solve. It's no longer a quadratic formula, it's just a regular old algebra, and we were able to solve a little bit easier, a little bit faster for this one. I hope you guys found that helpful.